Okay, thank you. Good afternoon, everyone. So my name is Jorge Coelho. I'm professor at the Chemical Engineering Department of the University of Coimbra and also belong to the directors of the Portuguese Society of Materials. And on behalf of the SPM, I would like to start by thank you everyone for attending our third webinar devoted to the research of excellence that is being carried out in Portugal and is financed by ERC grant. So today I have the honor and the privilege to introduce our invited speaker, Professor Adélio Mendes from Philp. Professor Adélio Mendes received his PhD degree from the University of Oporto in 1993. Currently is a full professor at the Chemical Engineering Department of the Faculty of Engineering of the University of Oporto. He's also an invited professor of the University of Harvard, a very prestigious university. By the way, is ranking on the 65th position of the Shanghai ranking. A real researcher, and also according to his former students, a very his research interests involve different areas: photovoltaic cells, dye sensitized solar cells. By the way, the topic of his ERC advanced grant, perovskite solar cells, photoelectric cells, electro reduction of CO2, electrolyzers, fuel cells, redox flow batteries, membranes, and carbon molecular sieve membranes. So Professor Adélio Mendes co-authored more than 400 articles in peer-reviewed international journals. He filed 25 families of patents and is also an author of a textbook about laboratory work in chemical engineering. He is co-author of the patent that has ever been licensed in Portugal with highest value. This patent describes a technology that was licensed to FASEC about laser-assisted glass encapsulation of glass cells. He was the recipient of an advanced research grant from the ERC on a project entitled Building Integrated Dye Sensitized Cells in 2013. He leads and has led several European Union projects, namely 2 future and emerging technology projects, which are among the most competitive ones. And the overall budget rose for his institution is the stunning number of over 25 million euros. So he naturally has received a lot of awards. I'm just going to cite some: the Air Products Faculty Excellence in 2011 in the United States, the Municipal Gold Medal of Merit from Oporto City Council in 2015, the Coimbra University Prizes in 2016, and presently he is the president of the VG Collab Energy Storage. He was also a co-founder of the Associação Rede Competência em Polímeros. And besides all of that, he is also a major entrepreneur. So he has been involved in the creation of several spin-offs, mainly with former students, which probably most of the people know is a reference company nowadays in equipment supply, CIS Advanced, Vis Blue, Aminaspur, Pixel Voltaic, and C++. So the title of today's seminar speaks by itself. So it's from a scientific dream to a great business, the story of dye sensitized cells in Portugal. At the end of the presentation, we have time for questions. So Adélio, thank you on behalf of the SPM. Thank you very much for accepting to be here with us. And so now it's your time. Thank you.
Good afternoon. I must acknowledge first Jorge Coelho for the invitation and for the organization of these conferences. Also Jorge Lino for the organization of these events, which are always opportunity for sharing ideas and exchanging ideas. So thank you for that. So I'm moving now for my presentation. So this is the story that was initiated in 2008. by the time the dean of the faculty, Professor Carlos Costa, challenged me for entering in a new area of the photovoltaics. And I choose dye sensitized solar cells because it was fashionable by the time, was something under the lights, so lots of publications. And but I was not acquainted to the background of photovoltaics or photoelectrochemistry. So how could I start doing research on that? That was my question. And then I suggested, because I read the articles and I realized that it was very important to encapsulate these cells, the cells that you can see here, and these dye sensitized cells, because they use liquid electrolytes. So it was really important for the stability of these cells to be properly encapsulated.
Bruno, para, sai daí, caramba, Bruno, por favor.
Não vai encher, fecha.
I realized that it was really necessary for a proper encapsulation. And by the time, the best encapsulation process was using polymers, which was not good enough. And so I met by chance the inventor of this new technology, Professor Michael Gratzel from EPFL in Lausanne, Switzerland. And I asked him if it will be a good idea to develop a glass a glass encapsulation process, which he said, yes, surely, go ahead. And so he motivated me. By the time, I didn't know that others tried hard to do the glass encapsulation and they failed. But I was too young for the topic, and so I embraced this challenge, and I start doing research, and we got eventually a first project approved in 2008 involving FASEC for laser-assisted glass encapsulation. By the time, we were not very aware of how to succeed that. So first of all, let's explain what is this different technology from many others that are now available for photovoltaics. So it uses a dye. So it's an organic or organic metal molecule. It's a dye which absorbs the light and injects an electron in the conduction band of a photoelectrode here. So you have titanium dioxide in this case, and so you inject an electron in the titanium dioxide conduction band, which goes around. And for regenerating this oxidized dye, we have an electrolyte which carries the charge, so transports electricity. And we have here normally a catalyst, which often is platinum. It's very simple construction. It's very nice because you can have very nice colors here, different colors. It's a different way to make photovoltaics. But they were invented in 1991, so 30 years ago. And by the time the highest power conversion efficiency report was about 7%. 30 years after, so this is Michael Gratzel, 30 years after, we have just the world record for lab devices, 13%. So you may ask, why waste time for developing a technology that is so inefficient? Why is that? Something over. Well, not exactly. If you go indoor, by chance, dye sensitized solar cells is the technology which displays the highest power conversion efficiency. So ourselves, we already reported 32% of power conversion efficiency, which is absolutely amazing and is above any other technology. But indoor, you have between 100 and 1,000 times less irradiance than outside. So all the powers that you can produce are much smaller. So I have here an example. So for indoor irradiance, you may have between 0.1 and 1 milliwatt per square centimeter. And so for a device of 100 square centimeters, you can produce between 3 and 30 milliwatts, assuming a power conversion efficiency of 30%, which, though it's very interesting, still quite low for producing power. Maybe it's not like that. One day, a couple of years ago, we realized that if we have an indoor photovoltaic, we can support the development of the Internet of Things. So I realized that we don't need to wire this switch to the lamp to switch on and off the lamp. So imagine that you have here photovoltaic cells that charge a battery inside, and this battery supplies the power that to power the wireless signal for switching on the light. And then I realized, because I was actually obliged to buy a battery during the pandemic, because the balance at home isn't the battery of the balance at home empty, and so I was obliged to go to buy a new battery, and I was pissed off, and I said, if I have here some photovoltaic cells, I will be able to power this balance for 20 years, probably even more. And when I use my iPhone, the battery is normally good for 1 or 2 hours. Maybe I can put, I measured myself, a photovoltaic cell and extend the life power of this battery. Instead of having it for 2 hours, I may have for 3 hours. And so I also realized that the Wi-Fi modules now, they use very little power. And so I will be able to supply the power needed using a combination between a photovoltaic panel and a battery. And let's see what competitors are doing. They are doing the same. Here is a fire alarm. This is for entering in a house. There are many applications that you can use photovoltaics, but none of these companies can provide devices that are stable for 30 years. And normally they are good for 3 years because they use polymer-based sealing system. I have here other examples. So what was necessary, what is necessary to do to make this technology fully commercial? That was our question. And we realized stability, efficiency, upscaling, aesthetics, they are crazy nice, and price. And so see how nice you can make a dye sensitized solar cell. This is crazy. You can put all the colors. You can use dyes. So stability. We came out with this idea of glass encapsulation with a laser assistant process. So this is the glass frit line that is used for glass encapsulate the cells. So we start firing the laser here, and this glass sealing line was heated up, melted, and after melting, got adhesion, starting cooling down, shrinking, cooling down, gaining the adhesion, cooling down, and breaking, obviously. It was not possible to glass encapsulate these systems unless we heat up the devices while they are being glass sealed. So we designed this machine. Actually was my brother, Joaquim Mendes, at the University of Porto that support us on designing this. He's from mechanical engineering. So we have here down an oven, and then we have a robot arm, and the laser head is somewhere there. And then we have a web camera just to see what how the glass encapsulation is progressing. The cell is here. You can see probably the cell down. It was being glass encapsulated. The problem is we had to heat up everything at 350 degrees C, while the melting point of this glass frit was about 400, 420 degrees C. That was not good. That was the beginning. Nobody, by the time, was able to do better. And by the time we realized that when we fired the laser, the temperature moved very quickly up and down. So from here to here, it was less than half of a second. And from here to here, it's probably 3 seconds. And then we came out with the idea of moving the laser forward and then backward.
Fazer o quê?
And then forward and backward again. And as you can see,
Sim.
as you can
Robô
see,
ainda não.
this pattern,
Robô ainda não.
okay. So the laser beam was moving forward and backward, but always moving, you know, a step forward. With this, we enlarged the time. The temperature was higher, and it was this that made possible the glass encapsulation. That was too high, the temperature. So we did research, and we start with 350. That was right. Then we moved down to 300, then to 250. Then we moved to 200. I still remember these times. Then 150, then 120, and now we can glass encapsulate at room temperature. That was the progress. That was, you know, nobody was believing on that. That was made possible because a great team that was put in place, because our imagination, and also because the money resources. We got actually plenty of money for doing that, and I must acknowledge that. But it was a fight. You see here again the cell there down for glass encapsulated. But as I explained, these cells use a liquid electrolyte with a low boiling point. So you use acetonitrile as a solvent normally here, so it's very low boiling point. And you introduce, after glass sealing, this small cell, this lab cell. Here is the area where you have the dye. You have to close these holes that are used to feed in the dye and the electrolyte. But obviously, this should also be glass encapsulated, but it was not possible to glass encapsulate at all. Why is that? Because when we fire a laser here, even using very low melting point glass frits, it was never possible to do that. And the reason was because as you fire the laser, the electrolyte starts evaporating, and you never succeed to do that. I try all possibilities that you can imagine. Nothing worked. We were desesperated. Well, meanwhile, we started developing the machine because we realized that the machine was absolutely critical. Otherwise, we start publishing all these achievements worldwide. And one of these days, someone in China will start producing the machine and we'll lose the lead. So eventually, 2 years ago, we start actually assembling this. And I had to acknowledge my brother again, but also a team from mechanical engineering that did and are doing a tremendous job on developing this machine. And this machine was possible to develop. And now we have a spin-off company, Pixel Voltaic, that is going to commercializing it. And they have already sold the first unit this year. So it's a fantastic advancement. Still, we have to address the holes. We have to seal the holes. So this is just a website image. We start sealing all these big devices, but always, as you can see here, it's very apparent, we use a very thin glass layer, glue it with a polymer. I was good for 45 dyes, as you can see, but eventually was necessary to develop a glass encapsulation process for the holes. And I must acknowledge a researcher working with me, Dmitry Ivanov. He got this tremendous idea that was, I'm going to move on doing that. We realized that we have a capillary here on the top. We could close this capillary without problems with the laser. So eventually we open this groove here. This is the hole, this is the hole. And then we fire the laser 45 degrees here. And we succeeded to close the holes, as you can see here. Very easy, no problems, fully closed. It was really an achievement. So we start performing some testing for assessing the permeability of this encapsulation. And we could realize that when you use sterling with a polymer for glass encapsulate, when we used a polymer to glass encapsulate cells and to encapsulate cells and the polymer to encapsulate the holes, the permeability of the cells were above the rejection limit. When we do the glass encapsulate of the cells, but we use a polymer for the holes, this was the leakage. When we did the glass sealing of the cells and of the holes, the leakage was equal to have nothing closed. So this is the minimum that you can get for permeability. So this is, we can say, the background permeability. So finally, the glass encapsulation process we developed was absolutely efficient for closing these devices. And that was the first ever achieved. So we ran for almost half a year an experiment with a cell just with polymers, encapsulated with polymers, with glass, but with the holes encapsulated with a polymer, and all of them were dead after some time. When we fully encapsulate everything with glass, it stay alive for this half a year. And what we observed was that this titanium dioxide mesoporous layer that I spoke at the beginning was being destroyed mechanically because the heating and cooling modulation or variation that these devices suffer in the aging chamber. So what we did was we improved the way we produce this mesoporous layer, and no longer we have such a problem now. So finally, we proved that our glass encapsulation process was really efficient for keeping these devices, for ages working. Concerning efficiency, as I mentioned before, the world record is 13%. And you can see here a distribution, a frequency distribution of articles reporting dye-sensitized solar cells. And you can see that most of the articles, they report devices of 8% of power conversion efficiency under sunlight illumination. So we decide to do a systematic optimization of all device using raw materials, commercial raw materials. So we optimized the blocking layer. We optimized what we call the transparent titanium oxide mesoporous layer. We also optimized the thickness of the reflecting titanium dioxide layer. And eventually we optimized everything systematically, and we arrived at the end to these amazing results. So 9.92 power conversion efficiency under sunlight, and at artificial room light almost 29% was a landmark. But doing research on that, we also realized that we could improve the efficiency of these devices if we use a substance that could prevent recombination. And in a collaboration, now not with the mechanical engineering department of the University of Porto, but with the University of Coimbra, actually with Jorge Coelho and Hermenio, we developed a new polymer that allows to prevent tremendously the recombination. By the time we achieved these power conversion efficiencies, 9 and 22%, but then we keep optimizing the devices, and eventually now we have this performance 11% under one sun light illumination and 32 for artificial illumination. And these are our record results for now. But we aim now to overpass the 13%. Let's see if we succeed. Let's wait for the results of next year. Upscaling. When you have a device, a small device like this one, you can get 6.7 of efficiency. But as you scale up, the efficiency goes down. The reason is because these devices, this glass, if you see the glass from the profile, here is the glass, and you have a very thin layer, about 700 nanometers layer that is named transparent conducting oxide. So it's a electrical conductive layer which is also transparent. It's conductive, but is not very conductive, and something should be done around. And so we came out with the idea of introducing these metal lines here for improving the current density, the decreasing the resistance. And as you can see, the resistance of the original glass with was very high, and as you introduce the metal lines, it reduces tremendously the resistance for the electrical conduction. But this metal line has not only to conduct electricity, it has to withstand at 500 degrees of temperature, because you have to sintering the photoelectrode of titanium dioxide, you have to sintering the glass sheet, and so it was important. But not only, because if you use, for instance, titanium, it's very good, but promotes the recombination, so destroys the performance of these cells. So it was necessary to do something around. So we tried several metals, and eventually we identified chromium as the best metal for this application, which displays no recombination effect at all. And as you can see in the IV curve, improved tremendously. So 194% that you increase the power conversion efficiency from no metal lines and with metal lines. So this is really an incredible advancement. So the identification of this approach. And so then we design other metal grids, as you can see, and now we are targeting this fractal metal grid, as you can see here. So with two thickness, larger and a smaller thickness. So we could reduce 10 times the electrical resistance of these substrates, aesthetics. So aesthetics is very important, but this is at EPFL, it's the Swiss Tech Convention, and you have these very large photovoltaic panels. The problem is, after 1 year only, they were leaking because they were not properly sealed. They were sealed with a polymer. We decide to move on, and now we are using glass substrates of 200 micrometers. And this is very good, for instance, for controls, TV controls, for instance, air conditioning controls that you can put there, and very thin devices. And eventually we work. Let's see if I can run this. What is going on? Okay, this is a house made of two colors, as you can see, and it can run this propeller or this fan just for demonstration at our lab. Okay, now I have to go ahead. Transparency and electrochromic. Transparency of Smith, transparency is very important because it's because the aesthetics. But it's also possible to combine these photovoltaic devices with the electrochromic effect. And we did that. So the cell, the Dye Sensitized Solar Cell is just this frame here. And it's able, upon illumination, to shade all this area. So it was demonstrated the possibility of using this device. This is just to show an array of these devices. You can use this for shading windows, but you also can use this for picturing things, so you can have images made of these electrochromic devices, but they combine very nicely. Price. For price, we decide to go monolithic. What is the difference from the conventional design and monolithic design? The monolithic design, you use the positive, the negative and positive poles are in the same glass substrate, while here it's in different glass substrates. And when you have different glass substrates, you have this glass here, the cover glass, that is quite expensive because it has this layer of transparent conduction oxide, while here it's a normal glass. Everything, not going into details, but everything is much easier if you go monolithic. The problem of monolithic is the performance were lower compared to this system. And so we decide to address also this challenge, and eventually we arrived to monolithic devices with a power conversion efficiency of 9.5 and for indoor illumination 22%. This originally uses a country electrode of carbon particles. We move on, and now we are using a PDOT, which is organic molecule, and we embed it in a metallic mesh, so we keep the transparency of these devices while the price is much lower. So, and we eventually improved a little bit more the efficiency. These efficiencies are world record. So this is the highest reported efficiencies for monolithic devices. The second best is something like 7-something%. So it's far away. So for concluding, I'd like to say that we addressed the efficiency, and now we have a power conversion efficiency of 11%, which is already closer to the world record of 13%. But as an advantage, uses only commercial materials. And our power conversion efficiency for indoor application is 32. And we are moving, we are now optimizing, keeping optimizing the devices using a monolithic design. Next step, we are going to address polymeric, fully polymeric based, so the substrates, instead of being glass or metals, will be polymeric, PET, so polyetherphthalate. We are now addressing this, and this is you know, a challenge that we are embracing, also in collaboration with the University of Coimbra. So nobody does the things alone. This is the team. Some faces are not here, some others are already left, but this is the team. Several projects. This was the advanced grant. It was 2 million euros. And now I want to advertise this conference, online conference, that is free of charge. Thank you. And now I'm waiting for the questions.
Okay, thank you very much, Deli, for the really amazing talk. So now I will invite the audience to ask questions to our speaker, please. We have time.
George, I don't know, I raised my hand. I don't know if it's necessary or not. But I'll go ahead.
Yeah, you can ask, please, Mahmoud, go ahead.
Okay. So first of all, thank you very much for the presentation. It's truly amazing to see in such a short time, from 2008 to now, you started from the basic research, reaching to the commercialization, and all of these publications and the report. My question is maybe very basic. I didn't understand what was exactly the problem of the polymers. I mean, fundamentally, that made you to move to the glass. And then my second question is, because your last slide, then you moved back to the polymer. So that was exactly where I wanted to ask why. Because one of the applications of the dye synthesized solar cells that people are pitching is being flexible. But as you say, it's not very efficient using the polymers. So where do you see really these two can join each other? So the efficiency of the glasses, glass-like efficiency, and polymer-like flexibility. Thank you.
Addressing the first question, why when using polymers for encapsulating these devices, they are not very stable, just because they permeate. If you permeate humidity to inside the cell, the water absorbs preferentially on the photoelectrode, on titanium dioxide, and so makes the dye to desorb. And as it desorbs, the cell is dead. Under solar irradiance, so this is also the problem. The electrolyte may leak out, and this happens when they are polymer encapsulated. And these are the two main reasons. Concerning the polymer-based cells, why we are addressing? Because price, because flexibility, but not because stability. What we are targeting is a stability of probably 3 years. For indoor applications, probably a little bit more. But this is the time frame that we are looking for. Well, if you glass encapsulate, you are looking for 30 years, 30 years, probably even more. So it's different things. So it's 10 times difference.
Okay, thank you very much.
Welcome.
Okay, thank you. More questions, please? Checking here, nobody else raised their hand. Okay, please go ahead. Raise the Lona, please.
Hi, Professor Adelio, can you hear me?
Yeah.
Yes, I can. Thank you.
Thanks. Well, first of all, congratulations for the presentation. Well, I'm from Brazil and I work with theoretical chemistry, researching about dyes used in this kind of solar cells. And I would like to know if ever you in your research group have found something interesting about these dyes and how could we improve them for better results with these solar cells?
We are not developing new dyes. We are using dyes that are commercially available, as I said. But obviously, we also, not being reporting new dyes, we studied the dyes and we study how we could improve the dyes. Up to now, what we did is combining dyes that absorb different parts of the spectrum. And when you combine, if you do this properly, you can actually improve the efficiency. So what is critically important in a dye? The band gap, it should be, the ideal band gap, it's around 1.1 electron volts. It could be around that, more or less, but around that. The other aspect is the energy level of the conduction band, or if you want, of the LUMO, because it must match with the conduction band of titanium dioxide. The other critical aspect is the stability must be stable. And finally, has to have a functional groups to anchor in the titanium dioxide particles. It should absorb strongly for conducting the electrons, the injected electrons towards the conduction band of titanium dioxide. And these are the requirements for the dyes.
Okay, okay. Thank you, Professor.
There is another one, sorry. If it has a very high absorbance, then you can make photoelectrode thinner, and so you can improve the conductivity of the photoelectrode.
Okay, thanks. Thank you very much.
If you want, you can ask by email, and we will be happy to help you in your research. So I guess you are not able to ask more questions now, but you can ask later on using email. You can ask other questions.
Thank you. More questions, please?
Good afternoon. Congratulations, Andelio. Very nice talk. I just wonder, you mentioned that you carried out some tests regarding accelerating aging.
Yep.
What do you mean by that?
We ran in aging chamber at 1000 watts per square meter, xenon light, and 45 degrees. I'm not sure about temperature, but it was around 45 degrees that we ran for half a year that we ran. Now we are doing this for more than 1 year. So we are running other tests, very long tests, because we want to have very long aging results. And the results are very encouraging because they are very flat.
Thank you.
So, Luis Pereira? Luis?
Yes, okay. Hi, Adelio. Thank you very much again for the nice presentation. Maybe just, I guess, maybe it could also be interesting for the audience and also for me, kind of clarification why these type of cells are they perform so nicely indoor comparing with outdoor. So we have such a big difference. So it has to do somehow with the type of dye, the cell construction, the type of wavelength that you have inside or indoor comparing to outside. So the spectrum of light. So
is the spectrum of the light that by chance the peak of power irradiance of this light, these artificial lights, overlaps to the maximum of the absorbance of the dyes that we are using. So this is the critical aspect. So you know that the fluorescence lights, they have peaks of emission light, and it happens that the peak of absorbance for this the dyes that we are using, they coincide, they overlap actually these emission wavelengths. So that's the trick. That's the reason why.
And did you see any big difference when you use LED lighting, for instance?
Both. So we test both LEDs, and we also test fluorescence. And it performs equally very nice. The difference is not great. It's a very small difference. It's mostly the same. So it's amazing because the dyes we are using are really fitting with the emission spectrum.
Okay, great. Thank you.
Okay, more questions, please? Just checking.
There is no more questions. I just would like to say something about companies, if you want to, if you allow me.
Sure, Adele, go ahead.
Why we start this and motivate to open this pixel voltaic company? Because I was developing things, patenting, and losing everything. Because big companies are not interested on that. It's something that they don't feel comfortable. And doesn't matter if it is national or international. I try both. Small companies, they don't have the money. So I decided probably I could make valorizing this research developments by motivating students of mine to start their own spin-off companies. And so far, we are having lots of success on doing so. So it was not only what I described. So now the machine is being sold. We have already orders from Michael Gratzel and from someone else. I can't remember. But as soon as Michael Gratzel will acquire one of these machines, Pixel Voltaic won't be able to deliver all the others orders. I'm sure about that. But we are also trying to commercializing, and I'm saying trying because it's necessary lots of money, so it's necessary to raise this money. It's what we are trying to do now, to develop these cells for making them commercial. Why you choose indoor applications? Because it's where they perform the best, but was not the only reason. Because these devices are small, and so the investment for kicking out the company was smaller. But you know, the ambition of the company is much larger than that. We start to go up stepwise, and so starting to sell what is easier for getting the money needed to commercialize what is more complicated. And suddenly, and now this Pixel Voltaic company is getting on board of European projects, which is crazy. It's really nice and is attracting, you know, research from Europe. So with these spin-off companies, we are not only internalizing the achievements, the research results we produced, but we are attracting research from other, mostly European countries. And so I realized that's fantastic. This is the way to go. And right now, I can tell you that 21% of the spin-off companies at the Faculty of Engineering, they were funded by ex or present students of mine. What we have now to do, it's a step forward. And I ask myself why a PhD student is allowed within the exclusive contract to give 4 hours of teaching, and is not able to do 4 hours to start a spin-off company. Why we are not starting you know, a program with postdoc grants for starting spin-off companies? Because the problem is, if you do not have these are, you know, disruptive advancements, it's not just an incremental development. It's something disruptive. So it needs lots of investment. But if you go with something that is very raw to investor, either you lose completely the capital of your company, or they are not going to give the money. What is the most important thing? Paying the salaries. These people that are, developing the companies, they also have wives or husbands and kids, and they have also to pay the bills. And sometimes all these programs that we do have in Portugal, they are designed for large companies to fund their research, but not for spin-offs, that sometimes they have no employees, or they have just 1 or 2 employees, and are the owners that are doing the job. And this job is tremendously difficult. So it's necessary for us to think the strategy for the development and to internalize the developments of the technology in Portugal, because we have now a scientific body of researchers that are quite good. There are problems, I know, but they are quite good. The problem now is the money we put in research, making this money to valorize or to pay back the taxpayers by starting new companies. And these new companies attracting actually the developments that are being performed abroad. And so this is the way to go. So I beg you to think about that and start a movement that will motivate the government, FCT, wherever, the innovation agency, exactly to change the rules and to allow Portugal to be a rich country.
Okay, well, thank you very much again for your amazing talk, your thoughts, your vision about how should we organize these technological transfers. So we are reaching the end of our webinar today. Just before finishing, I'd like to ask everyone to save the date for our next webinar. It will be on 26th of May. And we will have the privilege to have with us Professor João Mann, that I'm sure you know, it's a well-recognized scientist in the biomaterials. And I'm sure that everybody will have a lot to learn with him. So thank you very much for your presence in the webinar, and see you one of these days. Thank you very much.
Thank you.
Thank you, Adélio. Thank you very much for your nice presentation.
Thank you very much.